there are a lot of very good numerical algorithms to maximize or minimize functions. Now, the convention typically is that whenever you have a maximization problem, if you multiply your function by -1, it's equivalent to minimizing the minus of the function. The good news is people have looked at this a lot, and they've looked at this from several perspectives. From a mathematical perspective, people ask the question, well, can I use algorithm that would be efficient, and when can I prove that indeed these algorithms are good at finding the solution? From a more pragmatic perspective, people have thought about, can I find algorithms that are good enough that, for which I might not be able to prove that they converge, but that are very efficient? So these considerations are slightly different, but luckily for us, the key algorithm that people use are the same. And one of them is called gradient descent. We'll talk about that in more details. Another one is called stochastic gradient descent. We'll talk about that in more details too. And we'll talk about Newton's method. You might have seen them before in an optimization class. They're quite central to optimization theory. There are many variations of them out there, and they're pretty much used in one form or another in any machine learning problem. To appreciate what these algorithms are, understand they're trying to solve the following canonical problem. They're trying to say, given a function f, and at that stage, I'm not really telling you what f is or any property specifically of f, but the goal is to find the minimum of f of x over x here. I put in RD. Sometimes you might be able to constrain the set over which you're trying to find the minimizer. And the function f is defined as a d-dimensional, as a function that takes a d-dimensional input vector and outputs a real value. Okay, so it's not a function that outputs a vector, it outputs a scalar, but its input is a vector. And the idea of gradient descent is actually quite simple. It's saying, well, if I need to find the minimum of that function, let gravity do the job, and all I'm going to do is I'm going to follow the function by rolling downhill. And this analogy is actually coming from the following observation. If I plot a function, and here I'm plotting a function of a single variable, of course, to make it a little bit easier to draw, you might have a function that looks as follows. And on purpose, I'm not necessarily going to write a super nice function. And the idea of gradient descent is to say I'm going to take a ball here, and I'm going to let gravity pull my ball down so that my ball is going to roll down. And eventually it's going to stabilize in the point that is hopefully the global minimum, could be a local minimum. The goal is to get there. Well, what should be very clear from that little drawing here is that me saying I have to roll downhill is not enough in any way to prove that we converge, because you can convince yourself not to, without too much difficulty, that if I take a ball and I make it roll downhill from the left, I might very much get stuck here, which is a local minimum and not a global minimum. So in general, without additional qualifiers on the type of function that you're trying to minimize, it's going to be very hard to claim that algorithms are actually going to be able to find the optimal minimizer, the global minimizer. Now, thankfully, if you start saying that your function is convex, things are a lot easier. And the reason is because a convex function is a function that looks as follows. You might remember it as a function for which its second order derivative is positive. So that generalizes, and you can make that a little bit more formal. But essentially, it's always a function that looks like this. And this function have the very nice property, which is, again, not too hard to prove, but I decided not to do it in today's lecture, that any local minimum turns out to be a global minimum. And that's just a definition of, for definition of convexity, so that now if you roll a ball downhill, eventually gravity will pull you in the local minimum, which is a global one. And just so that we're on the same page, the definition of a convex function is just saying that if you take any 2 points here, which I'm going to call u and v, and if you draw the line that links u and v, the function is always below that chord that you're drawing. That's the definition of convexity. Turns out to imply a lot more that we can analyze very carefully. And in particular, under many circumstances, we can show that we can then prove convergence of the various algorithms that we might want to implement. So, very concretely, the way gradient descent works is as follows. You're going to start from a point. We're going to call that x0. That's your initial candidate as to what could be the minimizer of the function f of x. And then you're going to update to the next candidate simply by following the opposite direction of the gradient. So again, I don't intend that class to be a course in differential geometry, so let me just illustrate that very simply in the case of a real valued function. So f of x as a function of x. If I take a function, again, I don't necessarily make it nice, the gradient is always a vector that points in the direction where that function increases the most. So in our specific case here, if you find yourself at x0 right here, the gradient is going to be a vector pointing upwards. And what we're saying is we're saying here that our update to find a new candidate solution is going to be to take the gradient here at x0, multiply it by a scaling constant, which we call eta, it's called the step size, and put a negative sign on it. So the effect is to force us to roll downhill. If you were to put a plus, it's called gradient ascent, not gradient descent. And so in the specific example here, maybe you could say, okay, if I have a small eta, I'm going to make a small step in that direction. And as a result, your next point might be that point here, x1. And the hope is that by iterating that procedure many times, you eventually find the global minimum of the function. You keep going over and over until hopefully you converge. Under some conditions, as I mentioned before, one can prove that gradient descent will actually converge. That requires a bit of care, in particular because without putting more constraints on the kind of functions we're trying to minimize, this has no reason to work. And typical constraint that people like to make is saying, okay, well, I have a function that is Lipschitz, I have a function that is strongly convex. I will provide you more information on the side about these things. They're not critical for what we're trying to achieve in this course, but understand there's a whole theory about it. You might have to adapt the step size eta as a function of the number of iterations that you want to make. And you can imagine if eta is too big, you might end up in a situation where you never converge. Going back to my little drawing here, if you take a step size that is too large, you can imagine that you will always end up in a situation where your algorithm will jump. You take a large step size, your algorithm could jump here and then could back again, jump there, and you never actually converge to anything. If on the contrary, you take a step size that is very, very tiny, your updates take actually forever to move, and then it takes a very, very long time to find any good minimum of your function. So there's an art and a science behind that. I'm not going to go over too many details about this. Understand, people kind of know how to choose this. The step size eta, so that's the terminology that's coming from optimization in machine learning. People call that sometimes the learning rate. Understand also there are many variants of gradient descent. What I describe here is the absolute vanilla flavor that's behind all these algorithms. People have come up with many tricks to actually do this. I just want to mention a few just because that might give some of you ideas for the project that you'll have to do in this class. One variant of gradient descent is to say, I'm going to add momentum. It's called momentum gradient descent, and the idea is the following. If you keep the analogy of the ball that's rolling downhill, what we know is the ball has a mass, and the mass essentially means that even if you reach the minimum, you're going to go a bit further before you come back, and that's because you have momentum. That's a function of your mass. And the idea here is that you can modify the update that you are doing by not simply following the negative of the gradient with a specific step size, but here in that specific expression, actually keeping track of the speed that you had before in the form of Vt minus 1, your previous update, times the multiplicative factor gamma. Okay, so it has an extra parameter to tweak, but the idea is that you're keeping track of the momentum that you had going in a certain direction. And the update is otherwise pretty much the same, and you can show that under some conditions that actually performs fast, that converges faster than the vanilla flavor of gradient descent. And another form of this is called the accelerated gradient descent. So this one is very tricky. I think it's still an area of active research to really appreciate why that works and how it can be generalized. The idea is the following. You're going to keep the idea behind the momentum, but now, instead of evaluating the gradient at the point where you are, you're going to evaluate the gradient at the point where you think you're going to be. So that's why it's called accelerated. You're doing a prediction step in there. And you can, again, show that under some conditions, such algorithms perform extremely well. So if you start looking into the literature on convex optimization, you will be overwhelmed with variations about these techniques in different settings with different hypotheses. Of course, in high dimension, typically, it's a very active area. The reason I think the excitement is still there in that area is because these optimization techniques are absolutely fundamental. People use them not just to find the minimum of a negative log likelihood for logistic regression, as you can imagine, but they use that to optimize neural nets and train the weights in a neural network. And coming up with efficient algorithms that just perform a tiny bit faster means huge saving in terms of computational time and time for convergence potentially, and that's why they're so popular. So again, I will provide more information as to when gradient descent might actually converge. There's actually some really fun math, which is kind of very elegant in my opinion, because it's very visual and geometric, but I'm not going to do that in class today. Now, of course, one thing that we might have to be a little bit careful about is that to talk about gradient descent in the first place, you need to be able to evaluate the gradient. And if I give you an analytical function, you can compute it. But it could be that you end up in a situation where you don't have an analytical expression for the gradient, in which case you have to evaluate distance from the data itself, and things become a little more hairy.